Now that we've identified some of our shared ideas about what makes science teaching and learning effective, we're going to continue building on those ideas during the session, and we're going to do so through the lens of an instructional unit that comes from the middle school Open SciEd program. And this unit is part of a full curriculum for grades 6 to 8. It's 6.4, so that means it's the fourth unit in the sixth grade program. And just an important note, we picked this unit only because it's free and publicly available, and it was designed to include some of the research-based instructional changes that are the focus of our work in TXE. And so there's other good examples out there. This is just one example we're going to learn with for today. The other note is we designed this experience for you as learners so that this isn't exactly what students would do in a classroom. So we're gonna use some similar activities, but this is really designed for you as learners thinking about these shifts. So I'm gonna take a moment to connect to your pre-work activities and connect those to the learning plan for today's session. So you started by diving into this unit, what causes the Earth's surface to change. And you did so by watching a video about a scary event on Mount Everest that some climbers experienced. And we asked you to write down some noticings and wonderings while you watched the video. Then you were able to learn a bit more about Mount Everest and what happened during that scary day. We had you read that article, Earthquake in Nepal. And so you're going to have a chance to explore these questions and start to figure out what caused these changes on Mount Everest in a few minutes. But first, we want to come back to that video you watched. And we're going to give you some time to talk to some colleagues in the room and reflect on what you saw in the video. So we saw students in that video who actually were kind of on the same learning journey you were. They did some of the same activities leading up to that. And we asked you when you watched that video to record what the teacher was doing, what students were doing, and how you would describe the classroom culture. So take out your notes, take a minute to look back at your noticings and wonderings from the discussion. And so now that we've had a chance to take a peek into the classroom and discuss kind of what we saw students and the teacher doing, we're going to pick up and we're going to start putting together some of our initial ideas about what's going on with this event on Mount Everest and importantly, really what's causing this. So Joe, I'm going to turn it over to you.
Thank you so much, Jenny. Where we're going to head next is really thinking about what we know so far. So based on what you saw in the video and what you learned from the reading, we want to concentrate on what we know is happening with Mount Everest. So not so much wonderings and questioning right now, but facts. So if you would take a few minutes to relook over your notes from the article, if you need a second or two to pull them up, that's great. So look over your notes and then give us a couple of facts in the chat, one about Mount Everest and one about the earthquake. Give us the facts you know about Mount Everest. Last major earthquake was in 1934, and at that time, the mountain shrunk. Good, yeah, got it. Not necessarily about this earthquake, but it's definitely important information. Part of Himalayan. It's moving by 4 centimeters every year northeast. Yep. It moves each year. Getting taller every year. This earthquake didn't affect it height-wise, but it made it move. Fantastic. If you have more, keep putting them in, but we're going to summarize really quickly what's happening, what we believe is happening in terms of the movement, right? So for the first one, we know, and you mentioned it, that it's getting taller by 6 to 7 centimeters every year. We also know that it's moving to the northeast by 4 centimeters every year. Irregardless of the earthquake, this movement is happening, right? We also know that there was an earthquake in 2015. That's what we saw in the video when the hikers were so scared. And we know that during that earthquake, it didn't change the height, but it did move it by 3 centimeters back where it came from. So it's now, after this earthquake, right about where it started the year off, right? So based on what we know, now let's take a moment to capture some of our questions. So in the chat, if you would type one question you have about Mount Everest and one question you have about the earthquake, let's just see what kind of questions are coming up in our heads. How does this backward movement affect the plates? How can there be such a dramatic movement backwards? Good questions. Will this be consistent? If so, where will it be in 10 to 20 years? Really good question. Also another good question. Do earthquakes occur at all plate boundaries? Sensors. What could cause it to stop moving? Yeah, fantastic. So these questions, we will gather these questions and they help us to create our driving question board, which is going to help us to learn more and to drive our learning, to send us in the right direction for trying to help answer these answer the big question about what's happening on Mount Everest. So I appreciate you really giving us time for those questions, and we will come back to them later. The next thing we're going to try and do is take all the information we've just gained and try to synthesize a bit. And we're going to work like scientists and create a model to show and explain what we think is happening to make Mount Everest move. So in your model, you should be able to explain, to show, demonstrate, illustrate how Mount Everest moves and grows most of the time. So that general movement. You can use words and pictures to explain your thinking. You can include all of the components, meaning you have to be able to show how the mountains are moving. How are you going to show that? And how are you going to explain what you think the cause is? So include what you think is causing Mount Everest to grow and move. So these are the instructions for creating your model. These are individual. So we're going to go silent and solo for these next 4 minutes for you to make this model so that you can concentrate without any distractions and really get your thinking out on paper. We will share these models once the 4 minutes are up. So when we share and compare, here's the structure we're going to use to share out our thinking. And you'll again have a total of 4 minutes in your groups. Each partner shares and explains their model for about 1 minute each. Just be sure, since we're virtual, if you're not with a partner who's right there next to you, just be sure you're turning your work to the camera so that people can see what you're explaining. After you both share, then you want to compare your models and look for the similarities and differences. So when you see similarities in both of your models, on your own model, put a check mark by that spot or that aspect of it. If you see differences or things that you're not quite sure of, then you can put a question mark next to it. And we'll talk about these similarities and differences when you return from your breakout rooms. Thank you, everyone, for your contributions. Appreciate it. We are going to take another minute here to think a little bit more about the earthquake, right? So we had a concentration on the movement. We saw some of each other's ideas. And now we're going to think about what is that connection? Is there a connection maybe between the earthquake and the movement? Is there one? So let's look at this question about patterns. Do we think that the 2015 earthquake, is a random event or part of a pattern? Are there lots of earthquakes or very few earthquakes in this region? And let's think about how we could maybe find that out. What do you think? Where could we go to find out? What could we turn to find out if this was one earthquake as a random event or if there are many earthquakes happening? What might we look for? What kind of data do you think would help us? So scientists who study earthquakes, seismologists, have been tracking the occurrence of these earthquakes over time. So they know where they happen, they know how strong they are, the magnitude, and they know their depth. And they've been mapping them over many years. So this data was actually used to develop a simulation like the one that's on the screen that we're going to look at in a little bit more detail in just a second. So we're going to use this simulation and investigation, but first I want to give you some ideas about how this simulation works. So Anthony's going to click on it and take us to the Seismic Explorer. And first he's going to show us how you can zoom in right there on Mount Everest. Can you zoom in for us, Anthony? Right, so you can get closer, so you can see Mount Everest really, really well, and you can use the zoom in button to do that. Then this timing button across the bottom, right? The timing button across the bottom is slidable. You can look at any particular year you want as the earthquakes proceed, right? You can stop it anywhere you want along the way, and you can back it up. You can also just let it run if you prefer to do that, but you can move it to any particular place you want it to go in time. You might even want to try searching for the 2015 earthquake that was in April 25th, the one that we saw. You can also see the key up in the top right-hand corner. When you click on it, the size of the circles indicates the magnitude or the strength of the earthquake, and the colors represent the depth of the earthquake, right? And then the last thing we want to be able to manipulate, if you wish, is the magnitude bar across the bottom. So you can move it so you can narrow in on specific magnitudes, or you can make it so you only see magnitudes of, say, 5 or higher or lower, any way you want. So when you do this investigation, we'll talk more about it in just a second. When you do the investigation, those are some things you can use to manipulate the simulation to help you gain the information that you want. Anthony's found our earthquake. Cool. And when you click on one, it shows you what the information about a specific earthquake. So let's go see what our model is going to, what our simulation is going to entail. So you'll have 5 minutes to investigate the Seismic Explorer, and you'll want to take some notes about what you observe, because you're trying to answer this question. Is the earthquake on Mount Everest a random event or a pattern? How you go about that is up to you. This is your investigation. You'll do it individually. And then we'll come back and see what you think, whether you think there's a pattern involved or whether you think this was a random event, this one earthquake. Or actually you could say that this earthquake and the one in 1934.
So before the break, we were wearing our learner hats and we started to gather some ideas and make some models about with our ideas about what's happening on Mount Everest. And now we're going to put our teacher hats back on and head into a classroom and hear what students how their ideas are changing about what's happening on Mount Everest over time. And so as you watch this video, I'd like you to have your journal and a pen handy, and you're going to record some ideas about what you see the students doing, what you see the teachers doing or not, and what the classroom culture is like. And Anthony has just copied the transcript into chat, so I really encourage you to follow along as we watch the video, so you can capture sort of evidence of that connects to your observations. And so this is going to be a peek into a scientist circle. And just be prepared to share your ideas about what you notice and wonder from this classroom.
Can somebody share out not what they said was puzzling, but can you share out what your partner said was puzzling about their model as a way to show that we were absolutely listening to our partners? Radu, go ahead.
That the tectonic plates make it grow bigger.
What do you mean the tectonic plates?
So how they shift and it points it up and then the mountain grows.
So I heard you say it was puzzling, and who did you speak with?
Miles.
Okay, so it was puzzling about tectonic plates making something bigger. Is that what I heard you say? Great, thanks for sharing about Miles' work. Sophie.
So this is kind of, I had two partners, so
Great.
both of them said this. Kind of confusing how the tectonic plates actually worked and like what happened with the tectonic plates.
Okay, yeah, and to be honest with you too, that was a fancy word that I've heard some people saying and looking at people's initial models. Not everybody had that, so maybe that's something we have to figure out about too. Great, thanks for sharing, Toby. Toby, what'd your partner say?
I had two partners, and Ethan said thought that the snow came down and then it would push the mountain up because it would all catch at the bottom
Okay.
of the mountain. And then Noah said that it would be raised as the mountain was moving. So like the mountain might go up a hill, and that's how it would get taller.
Interesting. Those seem like different ideas, right? And that's interesting and puzzling too, right? And I see you guys laughing. Like, why are you laughing?
Ideas are not the best.
Hold on a second, but we have to recognize, like, I don't think anybody at this point, right, really knows how this works. We had a lot of questions about that, and even though your ideas are different ideas in our classroom okay? Yeah, I mean, think back to our thermal energy unit. None of us considered particle collisions at the beginning, and at the end, we were laughing about where we had gone, right? So it's totally okay. Some of you are smiling now. It's totally okay to have these ideas in the beginning, right? So thank you for sharing, okay? And what I'd like us to do is we're gonna actually build out an initial consensus model, okay? So remember that when we start this, we're gonna try and find things that we absolutely without doubt agree upon. And then, as I'm already hearing some puzzling stories being shared, it seems like we might have some disagreement, okay? And is disagreement okay? Absolutely, right? So we're gonna work towards that. And then we're also gonna try to think about, are there any kind of ideas out there that maybe as we share what we agree and disagree upon, that maybe new ideas emerge and we can consider them too, okay? So, let's see if I can do it this way. And this might be kind of crazy, we'll see. But, maybe it's here like this. Can you guys maybe all see this? Is this gonna right behind it? Okay, cool, great, it'll work. Awesome, so let's start. What are some things as a class we absolutely think that we probably agree on about this Mount Everest phenomenon? Like, what is hands down, like, we know? Janelle?
That it's moving northeast.
Okay, can I have everybody participate? Do we agree that the mountain is moving northeast?
Yes.
Thumbs up, thumbs down? Okay, unanimous? I don't have everybody participating. Okay, cool, great. So how do I draw that? How do you guys want me to show this? Anybody have any ideas? Go ahead, Karen.
So you draw one picture with the mountain here, and then like another one with the mountain here, and so on and so forth, I guess.
What's he saying? Mountain here, another mountain here.
Before and after.
Go ahead.
Like a before and after effect?
Is that what you mean, Karen? How do we feel about that? Before and after?
Yeah.
Yes, no? Okay, okay, cool. So a before and an after. Is that okay?
All right. So take another minute to jot down some of your ideas about what you saw the teacher doing, students doing, and what was classroom culture like. And make sure you reference your transcript. That concludes our sort of immersive learner experience, and we're going to have a chance in a minute to come back to some of those ideas about effective teaching and learning and think about what we might add to the list based on what we've done today. But what I first want to do is turn it over to Joe, who's going to take us and help us think a little bit about how this connects to our new 2024 TEKS. So Joe, take it away.
Thank you, ma'am. We really appreciate that you got this learner experience, that you were embedded in, and that you invested in the learner experience. And we want to take a moment to see how our new TEKS can really support this kind of instruction in a way that our current TEKS might not. So the first thing we want to do is look at this overview. This is a really quick overview of the changes in the TEKS. And I will tell you that on Resource Connect, there's a tool called TEKS Resource Tool that you can use to dive in much deeper to every content area and find out more about all of these standards and how they are changing and what's different about them. But for the overview, let's first look at content. So content is still structured in the way it has been in the past, with knowledge and skill statements supported by student expectations that detail out how that knowledge and skill is supposed to be acquired and mastered. They're still in their 4 content strands. Those haven't changed, just like our current strands reporting categories. We still have matter and energy, force, motion, and energy, earth and space, and organisms and environments in 6th through 8th, remembering this is 6th through 8th only. The changes there are that most of the knowledge and skill statements are revised, they're reworded. Many of the student expectations are shifted from one grade to another. We'll see that in a minute when we look a little bit more at the standards that support this particular lesson and unit. And so there's a lot of shifts going on and changes going on. None of them are hugely major, except that a few are added. There's some new knowledge and skill statements and student expectations that have not been there before, and some are removed. But in general, the content covers most of the same concepts as it currently does. When we look at scientific and engineering practices, basically what's happened here, yeah, we're going to stay on this slide for a while, Anthony, thank you. Basically what's happening here is that a lot of the same student expectations exist, but are reworded and reorganized. It's like we took all of our scientific investigation and reasoning. I'm so into 2024, I can't remember what we're doing now. The investigation and reasoning, we've taken most of those, kind of reorganized them, but kept the gist of a lot of them and added new. And they're organized into these 4 basic knowledge and skill statements that focus on planning and conducting investigations, evaluating and analyzing information and data, which was not clearly defined before, constructing and communicating explanations, which was also not clearly defined, and making connections to past and current research in STEM careers, which didn't exist before. So that's basically our new scientific and engineering practices. The most exciting part is the addition of this 3rd dimension, this 3rd domain, recurring themes and concepts. And these are basically captured and modeled after the same cross-cutting concepts that are in the K through 12 science framework. And so these are the 3 dimensions upon which now come 2024, our standards are based and all of our instruction can be based. So this gives such an exciting opportunity for me. This is the way I feel about it. It's an exciting opportunity to really stretch our instruction to be 3-dimensionally based. Not that I don't think there are people out there, districts and classrooms, that aren't currently trying to work through 3-dimensional instruction. There are, but the standards we currently have don't support it. It's like having a 2-legged stool instead of a 3-legged one. And now we will have that 3-legged stool and be able to really branch out and deepen our instruction and make it much more impactful, much like the lesson you just experienced. So now that we've thought about that, let's really think about how our new standards could map to a unit like this one. So we're going to look first at the unit level and see how the 3 dimensions work here. And then we're going to look at a lesson, a learning target, a lesson target level. So let's look at the first one, the content. Here are the 3 standards of the 2024, the new standards, that map most closely to this particular unit. And the lesson you experienced is the anchor phenomenon introduction to an entire unit that's based and structured on 3-dimensional standards. And that's why this map kind of works much better than what we have currently. So in this one, it's really the 7.10b that maps the closest. And while the lesson we experienced doesn't actually get directly to plate tectonics right away, that's part of the mystery and the excitement that's built around this particular anchor phenomenon. Please notice that this is a standard that used to be, or currently is, sorry, approached in 6th and 8th grades, and now will be moved to 7th grade. So there's an example of how things are shifting around. Great, let's look at the scientific and engineering practices. Here you can see that these are mapped. Basically, this is not all of our scientific and engineering practices. These are the ones that are more focused on in this particular unit. And then the 3 that are coming up circle are the ones that mostly you saw in the lesson that you experienced. So, but you can see how in just that lesson, at least 3 of these practices are being put into play, and students are literally involved in doing them. And many of you mentioned doing the science, being involved in the science, and this gives you an example of how that can work. So there's lots of them out there that could be used in the rest of the unit. These are the 3 that we mostly saw. Now let's take a look at our recurring themes. Again, there are several that were approached in this particular lesson, touched on in this lesson. These are the ones that are the greater focus for the unit. We'll look in a minute about how some of these can work within the lesson. But looking at these 3, the content, the SEEPs, and the RTCs, as we've nicknamed them, these 3 dimensions together can create a much richer, fuller, deeper, more impactful unit than we might otherwise be able to do, trying to work only 2-dimensionally. So let's take a quick look at what a lesson target might look like in a 3-dimensional manner. This is the actual lesson target for the one from OpenSciEd. And you can see that they have color-coded it to show how the lesson target can reflect all 3 dimensions. This is not, by the way, however, an objective you would necessarily put up on the board. This is a target for the instructors to be able to understand where they're trying to take kids in a particular lesson. But as you can see, the blue indicates this was the practice that we used when we were modeling. The green indicates the recurring themes and concepts that were touched on when we tried to do our model and when we tried to do the investigation. And then the core content is the orange. And if we look again very closely, we do the next slide, we'll see specifically how they relate to those standards we just took a quick look at. Okay, I know that was a lot. But it gives you an idea of how we can really work with these in a 3-dimensional way and how they sort of open up some doors for us that might not have been there before as we as instructors work to try and really create meaningful, impactful experiences for our students. I think one question you guys might be having, at least I would be at this point, is, and you all mentioned it, in how do we really structure this? How do we get our classes to the point, what strategies and teacher moves can we use to help us really set this kind of learning in place? And so the next thing we're going to do is work through some articles in a jigsaw structure. And this, if you're all working, if you're not working independently, it might be a little bit different. You'll end up in different groups, but we'll make the best of it. And so what we're going to try and do here is work through these 5 articles. Each person in the group will choose an article to read, and then we'll share out and share what our thinking is about each of those articles and how they relate to these 2 questions. How does this support an equitable classroom culture where all students have access? And how does this support students in figuring out the phenomenon? So again, there are 5 different articles meant to really kind of connect directly to the lesson experience that you saw. So there's examples of each of them within that lesson experience for